All right, thank you. So those were the two invited talks. So our next one will be by Evangelos Papoutsellis. Evangelos has been working with CCPI and Synerby for a long time and has worked a lot on stochastic optimization techniques, and is going to present the latest observations and conclusions and experiments on making that even better. Thank you, Evangelos.
Thank you very much for the introduction. Yes, my talk is split, skip, and play for tomography reconstruction. So it's mostly on optimization and CT, and it's joint work with Zeljko Kereta and Kostas Papoutsellis. So my talk will try to answer these two questions, these fundamental questions. So why do we use all the data in every iteration for tomography reconstruction? And the second is, why do we apply the regularizer in every iteration? Why do we apply TV in every iteration, or draw BM3D, or some pre-trained denoiser? So the left is focused on the split term, and the second is for the skip test. So just to set up the optimization framework, we have these this minimization of two functions. Both of them are convex, and F is ellipsis smooth. And we basically have this algorithm, proximal gradient descent, or ISTA, or forward-backward splitting, which after a gradient descent step, we apply the proximal. And for the G, we can have a proximal type of function, which can have a closed form solution, or we can use an iterative solution, for example, using the total variation function. Now, in this talk, we have this kind of proc skip algorithm, it's called, introduced in 2023 for federated learning applications. And the idea is that basically we don't need to use the proximal operator in every iteration. So we have a probability P and a control variable H. And first, in step 4, we do a shifted gradient descent step. It's an anchor point. And then we flip a coin and we decide if we want to prox or if we don't want to prox. If we don't want to prox, we save some time, we don't do anything. But the moment we decide to do the proximal operator here, we are trying to correct with this control variable. The most important thing in this algorithm is not that we skip, is that we skip and correct. And let's go back to the standard TV denoising problem on a 2D small grayscale imaging. So we have the ground truth, a noisy image, and this is a TV denoising result. And we solve this very famous problem, the Rodino-Fatemi minimization problem, using this dual representation. So everything is smooth here, and we basically apply a gradient descent step. And we have this PC, which is a projection operation with these three mathematical operations: division, the L2 norm, and the maximum. And after we iterate for k iterations, we use this equation to obtain the denoised image. So this is what we get if we use different kind of probabilities. It's not a very interesting plot, except, okay, for the very small probability, we have a lot of oscillations because we skip these projection steps, and after 10,000 iterations, everything matches. And this is if we compare the error versus the iterations. However, it's a totally different story. If we compare the error with time, we see that the one that had a lot of oscillations actually reached this target accuracy in like 42 seconds, and we use only 400 projection steps. So it's quite fast. But this is a TV denoising problem. Let's go. Why it is the reason why it behaves like this is because, okay, this for the first 100 iterations, we apply the projection step only here, but then we delay it a lot randomly. We cannot be sure when we apply the projection. So that's why here we start to see this divergence. But the moment we do the projection step, we correct and we try to match with the proximal gradient descent or ISTA. And the important thing to note here is that, okay, this is doesn't cost a lot here, but the important thing is how much the projection step cost relatively to the gradient of step. If we go to more heavy proximals, like for total variation 2D tomography reconstruction, we're solving this kind of problem. And for the proximal of G, we use an iterative solver, similar to the DVD noising. So we use accelerated projective gradient descent or FISTA, so instead of momentum reconstruction. And for this type of solver, we either use 10 or 100 iterations. So we have some inexactness of how you solve TV. Again, for 10 iterations, we see that in terms of iterations, error iterations, the plots are the same. We cannot beat yet FISTA for this type of, for this 10 to the minus 3 accuracy. And if we focus in the time, we see that the blue, the small probability, is going the fastest. And also notice that at FISTA, we cannot reach the very low accuracy 10 to the minus 5 because we have these inaccuracies, how we solve TV. If we increase to 100 iterations, everything looks good. FISTA is quite slow, and the blue one with probability 0.1 is the fastest one. So the idea is not now to use all the data, but split our data. If we have this kind of sinogram, we split our sinogram into subsets. N is the subsets. So we have this f of x, and we have a finite sum representation. And the idea is to use this proximal proc-skip algorithm, and the only change that we are doing is replace this gradient of f with a stochastic estimator of this gradient. And this can be any stochastic oracle, stochastic gradient descent, SAGA, SVRG, and LSVRG. I will not go into these details, but basically for SVRG and LSVRG, we compute stochastic gradients and we try to correct at some point using full gradient computation. Here you will see what is happening in the first few iterations. This is the data pass, means that we saw all the data in some iterations. So in proximal stochastic gradient descent, we have all these stochastic gradients, which are kind of noise. And as you can see, the proximal step costs something here. But when we go to the skip version of that, you will see a lot of zeros, means that we didn't do anything. We just copy the image and we didn't do the proximal. And if we do the SVRG, which is tries to correct these stochastic gradients, we can see something better in the gradient space here after some data passes. And for this experiment, we played two games. The first game is that we have a reference solution that we computed, and we have an accuracy epsilon. And the second is we have, and we work with real data sets, and here is a simulated data set. And we loop from with different number of subsets and probabilities. And for BM3D, as a plug-and-play application, we fixed a time budget of 3 minutes. And initially, we had 72 seconds for FISTA, and we couldn't beat proc-skip because it was 162 seconds for this type of target accuracy. But now we went to 11 seconds using the split and skip approach. Also, we are better in terms of the standard stochastic optimization techniques that they do not skip in every iteration. And here is the BM3D example. So as you can see on the left, if we compare SSIM with iteration, we see why FISTA is called FISTA. It's fast in the beginning, but it's totally opposite when we compare SSIM with respect to time. And yeah, and I try to do that with 3D on a tomography reconstruction. It works on my laptop, and I use fixed time budget for every algorithm. I was quite surprised that actually worked on my laptop, but anyway, yeah, no, use only 10 iterations for TV. And yeah, you can see that the green one, the prox SGD skip, is quite fast but not stable as we iterate, as we reach the 10 minutes, but it's better than Vista and the prox SVRG. Yeah, to conclude, data sampling and random skipping can preserve convergence first of all, and provide some significant speed up for tomography reconstruction. And working now on trying this plug and play with pre-trained denoiser. Also, instead of skipping a non-smooth term, we can apply this with like gradient skip for smooth regularizer. And initially, we tried something with Edo for the Petric challenge. It seemed to work. But okay, the amazing thing is that all of these results that I presented, you cannot reproduce, first of all. You need my laptop to reproduce them. Especially you need, for the time plots. But you can try this with Binder and Google Colab. And notice in Binder that it takes one iteration, the one BM3D call, 20 seconds to do, and you have a limited amount of memory, and also you have a limited time of how you your binder kernel is open. So this approach with different operating system works with the splitting and the skipping. Yeah, thank you for your attention.